So yeah, so this is an introduction to the themes of the workshop, namely the distortion and the trade-offs between information and efficiency. And the purpose of this talk is to make people familiar about this work, people that have not necessarily worked on similar topics before, but also what I will try to do is to kind of connect all the different talks that you will see in the workshop, all the different themes, and explain how all of these can be interpreted under kind of the same umbrella. So let's get right to it. So I will start with a very simple example, a motivating example, which I call gather or breakout rooms. So imagine that the diet organizing committee is trying to decide, so they would like to decide whether to have the breaks on gather or in breakout rooms on Zoom. And in order to decide that, they ask the participants for their inputs, and they ask the participants to declare which ones they prefer. Now, you know, this is obviously a hypothetical question because we never did that. We were not that democratic. But let's say for the sake of the presentation that we did. And let's also say that the option that received the most votes was actually breakout rooms. So this is what happened ultimately. Let's imagine now that instead of just asking people to give us their preference, we also ask them to write a short comment explaining the reason for choosing the option that they chose. So the first person, first I will present the comments of the people that voted in favor of the breakout rooms, followed by the comments of the people that voted in favor of gather. So the first participant said, I like both options. I have a very slight preference for the breakout rooms. The second participant said, I don't really plan on talking to anyone. I don't care. I have to vote for something. Well, I just vote for breakout rooms. And so on until the last participant in the first group that said, well, I'm not really familiar with either of those options. I'll just vote for breakout rooms. And as you can see here, for this first group of people, these people are not very strongly opinionated, but they constitute a very weak majority. And this is why this option is the one that won the vote. But if we look at the options of other people, the people that voted for gather, we had something like this. Gather is amazing. We should definitely do it there. I really hate breakout rooms. You just get matched to random people. I want to talk to people that I know. Go for gather, gather all the way. So on and so forth. Please do it on gather. So what this example demonstrates is that if we actually knew some more information about the preferences of the agents, if we had these comments, then we would realize that we actually made the wrong choice. And this is what the example conveys, that if a decision is made based only on ordinal information, which is information that has to do with comparisons between the different things that can happen, then this might not be the right thing for society. And the fundamental question here is, if we made the wrong choice, how wrong is this choice? In other words, how much worse can this decision be when we compare it to the fully informed one? So what is the fully informed decision? Well, in the context of the example that I showed you before, it is basically the decision that we would have made if we had access to the comments as well as the preferences. More generally and a bit more formally, we will assume that there are some underlying cardinal valuations, some cardinal information that the participants have for all the different outcomes. And these are numerical values, which indicate not only which outcomes they prefer to which, but also by how much. And this is what I mean by the intensity of the preferences there. The point is that we do not have access to this information, but this information exists. And then the answer to this fundamental question here is measured by the notion of the distortion, which is central to the theme of this workshop. And it was introduced by Procaccia and Rosenstein in 2006. Let me make things a little bit more concrete. And let me start by introducing the basic setting. In the basic setting, we have N agents and M alternatives. And sometimes we will call the agents voters, and the alternatives, we will call them candidates. And I have to emphasize here that although we're using the terminology from voting, this doesn't have to be about voting necessarily. It can be about any decision-making scenario in which there is a set of participants who are trying to somehow reach a consensus. As I explained before, we have cardinal valuations. So every agent has a value, uij for alternative j, which indicates the level of happiness, let's say, if that alternative was elected. And sometimes equivalently, we can refer to these as valuation functions, mapping alternatives to real numbers. And then in the most natural way, these cardinal valuations actually induce the ordinal preferences. These are preference rankings in which if the value of an agent for an alternative A is larger than the value of the agent for an alternative B, then the agent prefers A to B in the preference ranking. Simple as that. Now, an ordinal mechanism actually has access not to the cardinal valuations, but to the ordinal preferences, and uses that as input to output a single alternative, which is the winner of this decision-making process. And I will use the term mechanisms to refer to these functions throughout this talk, but throughout the workshop in general, you might see them referred to as voting rules, social choice functions, perhaps other names as well. So let me add one more thing to this setting before I proceed. So we will not assume anything about these valuations or these valuation functions. They can really be arbitrary, except we will impose a standard normalization, which we call unit sum normalization. So what this means basically is that the sum of utilities or values that an agent has for the different alternatives is 1. And this is true for all agents. And I will refer to this as the normalized setting. Now, earlier, I mentioned that what we actually did might have been bad for society because we didn't have enough information. But this brings forward the fundamental question again, what is actually good for society? You know, this is a difficult question to answer, and it has many different answers. And it's rather philosophical if you think about it. So for the purpose of this talk, and actually for most of the presentations during the workshop, with a few notable exceptions, of course, we will consider something to be good for society when it maximizes the utilitarian social welfare. And what is this? This is just the sum of the agent's values from some alternative. So the alternative that actually maximizes this quantity is the best thing for society. And again, just to make sure that we are all on the same page, if we had access to these values explicitly, then maximizing social welfare would be trivial. This is not a problem. We only have access to the preference orderings though, so we only have the ordinal information. And then the question is, how well can we approximate this cardinal objective, having access only to the ordinal information? And this brings us to the original notion of the distortion, as defined by Procaci and Rosenstein. And the distortion measures exactly this. So I call this the original notion because I will refine this notion in a few slides. And I will refine it just slightly, but I will argue that with this slide modification, we can actually capture many related problems that we can study under the same umbrella. So here I have included a semi-formal definition of the distortion. So the distortion of an ordinal mechanism is the maximum ratio, where the maximum is taken over possible inputs, of the maximum possible social welfare over the social welfare for which is achieved by the mechanism. And here I have to clarify that when I say over possible inputs, I mean inputs to the problem and not inputs to the mechanism. So as you can see there in this fraction, in the numerator, we have the social welfare of U. So U is actually the profile of numerical values. So this is the cardinal information. Whereas if we look at the denominator, the input to the mechanism is just the preference orderings which are induced by this cardinal profile. So this is the thing in the parentheses there. So the optimal and the mechanism have a different input, and this is the challenge here. Hopefully you're still with me, but if not, I will try to mend things with this picture here, where I have basically summarized everything that I have said. So let me go over this picture quickly. So there in the middle, we have the agents, and then these agents have some cardinal values over the alternatives. Using these cardinal values, we can actually find the optimal alternative, which is the one that maximizes the social welfare. And at the same time, these cardinal values induce ordinal preferences. In turn, these ordinal preferences are inputted by a mechanism, and the mechanism outputs some alternative, which doesn't have to be the same as the optimal alternative. Actually, typically, it won't be. Then we can calculate the distortion of the mechanism on this particular instance, this particular input, this set of cardinal values up there, in the same way that I described earlier. And then to find the distortion of the mechanism, we just take the worst case over all the possible cardinal values that we can have. And this is the definition. And coming back to the definition of the setting, I called it the normalized setting before. Now we'll call it the normalized utilitarian setting. And this is because I have now added that the objective is to maximize the social welfare, and the goal is to find the mechanism with the smallest possible distortion with regard to this objective. So this is the basic setting that I will talk about through the next slides. Okay, so let me talk about some mechanisms now. And before I do, let me make a distinction. So what I have defined as a mechanism so far is what we actually call a deterministic mechanism, where the output is a single alternative. But the mechanisms can also be randomized, and in this case, the outcome is a probability distribution over the alternatives. In particular, if we look at Pj is the probability that alternative J is selected. And of course, then, since we're using randomization, we can measure the distortion using the expected social welfare. Now for some examples of mechanisms. And to those of you who are familiar with the literature on voting, you will also be familiar with examples that I will provide here. But for the others, let me start from the simplest thing that you can do. The simplest thing that you can do is to choose an alternative uniformly at random, completely ignoring the inputs of the agents, just making a decision at random. And you might actually think that this is a pretty bad idea, because I'm trying to convince you that we are impaired by the lack of information. We only have this ordinal information, and we're even ignoring that. But you might be surprised by this mechanism, because you will see multiple instances where this mechanism, in combination with other mechanisms, can actually give you something meaningful. Another one is plurality. So this is also quite simple. This is deterministic, and it selects the alternative that most frequently appears in the first position of the preference ranking of the agents. Slightly more complicated, we have the Borda mechanism. So this mechanism selects the alternative that has the maximum Borda score. What is the Borda score? So the Borda score is calculated as follows. We look at an agent, and the most preferred alternative of this agent receives a score of m-1, where m is the number of alternatives. The second choice receives a score of m-2, and so on, until the last choice receives basically a score of 0. So this is the Borda score, and then we maximize the alternative that has the maximum Borda score. So this is a scoring rule, a scoring mechanism, but it's not the only scoring mechanism. Another example is the harmonic scoring mechanism, which does a very similar thing, but instead of giving Borda scores to the alternatives, it assigns harmonic scores. So the top alternative for an agent receives a score of 1, the second choice gets 1/2, the third choice gets 1/3, and so on. And finally, let me present another mechanism which is slightly more involved. And this is a randomized mechanism, which is called proportional harmonic. Actually, I'm not sure it's called that. I just used this name for the presentation. And here what happens is that, again, we compute the harmonic scores, but instead of selecting the alternative with the maximum harmonic score, we select every alternative J with probability proportional to their harmonic scores. So this is it. This is by no means a complete list. There are many other mechanisms, and you will see many other mechanisms throughout the workshop. But this list is actually enough for the things that I want to present in the next 4 or 5 slides. Okay, so let me give you some results about this basic setting that I introduced earlier. And I will actually give you 4 bounds, 2 lower bounds and 2 upper bounds, for deterministic mechanisms and for randomized mechanisms. So let's start with the upper bound on the distortion of plurality. So the upper bound of the distortion of plurality is actually asymptotically m². where again, M is the number of alternatives. This is fairly easy to see because you can see that the plurality winner, by the definition, appears first in the first position in at least N over M preference orderings of the agents. Then let's try to find the smallest possible welfare that it can have. Because it appears in some first positions, for those positions, the smallest value that you can assign is 1 over M. And this follows from the unit sum normalization. You cannot make the first position less valuable than this. At the same time, because we have unit sum normalization, there is an upper bound on the optimal as well, and this is N. And if you put the numbers down, then you get this bound. So the next question, of course, is, can we do something better than this? And it was proven in this paper by Yanis, Raprava, Ariel, and Nisarg that this is actually not possible. There is a matching lower bound for the distortion of any deterministic mechanism. And I have the idea of the proof here that I will go over. I have to say that this is slightly different from the proof in that paper, because the proof in that paper, so the proof of this statement in that paper is a special case of the much more general proof. So I have changed the proof slightly to apply to this, only to this case. Okay, so what do we do? So I will show you only the rankings of the agents for the first and the second position. And then from positions 3 and lower, I don't really care what happens. Now for the first position, I will partition the agents into groups of roughly N over M agents in each group. And for each group, the agents will place a different alternative, will rank a different alternative in the first position. So for example, for the first group that you see in the upper left corner, the most preferred alternative for these agents is the blue alternative. Then we have other sets of agents, and then finally the last set of agent places the yellow alternative as the top alternative. And across the groups, there is no alternative that is placed top in two different groups. So every group has a different alternative placed in the first position. Now for the second positions, all of the agents place one of two alternatives in that position, either the red one or the green one. And half of them place the red one in the second position, and half of them place the green one in the second position. Okay, so this is what the mechanism sees. This is the ordinal profile. This is what the input to the mechanism is, together with the rest of the, from positions 3 and below, which we don't really care what they are. So in order to prove a lower bound, what we will do is that for any possible choice of the mechanism, we will construct underlying numerical values that are consistent with this thing that we see there on the left, and that will give us a bad distortion. So let's consider the first case, and in the first case, one of the alternatives that appears in one of the first positions of the agents wins. And let's assume without the loss of generality that this is the blue alternative there. So what we can do is that for the agents of the first group, we can set their value for the blue alternative to be 1 over M. And consecutively, their value for everything will be 1 over M by this choice due to the unit sum normalization. Then for all the other agents that do not have the blue alternative in their first position or the second position, which is the rest of the agents, we will actually set their value for the first position to be a half and the second position to be a half. This particularly means that their value for the blue alternative is 0. And it also means that there exists some alternative, which is the green one in this case, that gets a constant value a half, from at least half of the agents. And if we put everything together, we see that the social welfare of the blue alternative is small, whereas the social welfare of the green alternative is large, and we get the lower bound in this case. The second case is when the red alternative wins, or some other alternative actually, which is not in the first position. This is much easier because we can select the numbers appropriately for this alternative to receive 0 value from the agents. And then we have, because we can actually achieve positive welfare, we have an unbounded ratio. So what about randomized mechanisms? This is the next question. Can we actually do better? And the answer is yes, we can do better, but not better than square root of M asymptotically. And this was proven in this paper by Boutillier et al. In 2015. And the proof is also fairly simple, so I have included the idea here. So what we do now is that we again partition the agents into groups, and we have square root of m groups of agents. And every group contains n over square root of m agents. Now, the agents of each group rank a different alternative in the first position, and there's no overlap across the groups. And we don't care what happens with the alternatives in positions 2 and below. It won't be relevant for the argument. Now, there is a very simple argument that has to do with how you distribute the probability mass that says that among these alternatives that appear in these first positions, one of them must receive probability at most 1 over square root of m. And let's assume without loss of generality that this is actually the blue alternative. Again, we will fix some values underneath to make this actually a bad instance. So what we will do is that for the first group of agents, there on the upper left corner, we will set their value for the blue alternative to be 1 and 0 for everything else. And for all other agents, we will set their value to be 1 over m for alternatives. So basically what we did here is that we made the blue alternative to be good and all the other alternatives to be bad. And because the probability that we select a good alternative is small, this is why we get a small welfare. So what we have is that the social welfare of the blue is large, whereas the social welfare of anything else is small. And then the expected social welfare of the mechanism, because it selects the blue one with a very small probability, at most 1 of square root of m, is small, whereas the optimal social welfare is large. And then we get the bound. Okay, so I showed you 2 lower bounds and 1 upper bound. So now we'll show you the final upper bound without the proof here. Let's consider the following mechanism. This mechanism will be a convex combination of 2 different randomized mechanisms, and it will select each one of them with probability 1/2. The first one is this uniform at random mechanism that I mentioned before as not really being a good idea, but here it seems that it covers some of the cases that the other part of the mechanism doesn't. And the other part, again with probability 1/2, is the proportional harmonic mechanism that I showed you before. So what this mechanism achieves, as it was proven in this paper by Boutillier et al., is a distortion of asymptotically square root of m log m. This is quite close to the lower bound. It's not quite there yet, but in the same paper, the authors have another mechanism, which is somewhat more involved, which achieves an upper bound of square root of m times the iterated log of m, which is effectively the same as the lower bound. It's effectively matching the lower bound. The log star of m is very close to being a constant. So summarizing the results for the normalized utilitarian setting, for the deterministic case, the distortion is m squared asymptotically. For the randomized case, it's effectively square root of m. So this is what we know about what I would call the basic setting, the setting where everything started from. But there are multiple extensions, and I will mention some of them now. So the first extension, perhaps the most natural thing that somebody can think of, is to elect a committee instead of a single alternative. And then, of course, if you would like to elect a committee, you have to define the utility of an agent for the committee, and you can define this as being either, for example, the maximum of their value for any member of the committee. It could also be the sum of the values. You can make other choices as well. Another very interesting extension is participatory budgeting. So what happens here is that every alternative is associated with a cost. And the goal is to select a set of alternatives that are within a budget. So not everything is feasible. We have to select something that is feasible, but we also want to minimize the distortion as much as possible. And I will not mention more about this because Gertus will actually give a talk on this paper, on this very paper on Friday. So make sure not to miss that one. Now kind of turning a leaf and going into a new chapter. So what I mentioned before in the normalized utilitarian setting is that other than the unit sum normalization, there was really no structural restriction to the values that these UIJs, that these cardinal valuations can get. But here, sometimes it makes sense to impose some restrictions and have some more structured domains. And one of these domains that makes a lot of sense is the domain of metric preferences, in which we can study under the distortion framework. And then, I call this metric distortion. So what happens here is that agents and alternatives, they're embedded into a metric space. And these cardinal values that I mentioned before, they're given by the distances from the different points. So in this example that I have here, we have the agents in blue, we have the alternatives in red. You see the distances, but what the mechanism actually sees is not the metric space, but just the preference orderings that are induced by this metric space. So I will not talk, there is a lot of work on this, a lot of work on the distortion on this. I will not say anything more here because we have actually dedicated a whole day to this tomorrow, starting with Elliot's talk, which will also give you an overview of this particular notion of distortion with metric preferences. So tune in tomorrow and you will find more, and also about some very recent exciting results. What I will say though is that all the things that I will present from now on, they can actually apply to the normalized utilitarian setting. They can also apply to the metric setting. Okay, so I promised you earlier in the presentation that I will redefine the notion of distortion or refine the notion of distortion. So the question was, how well can we approximate the cardinal objective having access only to ordinal information? So let me rephrase this sentence ever so slightly to the following. How well can we approximate the cardinal objective having access to limited information? And now you can see that, this is intentionally left vague here, but limited information can have a lot of different interpretations. One interpretation, for example, is ordinal information, and then we recover precisely the previous definition. It could also be less than ordinal information, because there are cases where this makes sense as well. Maybe we don't have access to the complete rankings. Or it can mean a little bit more than ordinal information, so maybe ordinal information and some cardinal information. It could also mean information that is not really classified as ordinal or cardinal, it's just information about the preferences of the agents that we elicit somehow. And finally, it could also be limited information that doesn't have to do anything with the preferences, and it's limited because of the structure of the problem. So I will try to give you examples about all of the things that I said, and I will connect them to the different talks that you will see throughout the workshop. But before I do that, let me just point again to the semi-formal definition that I have given for the distortion. And here you see that the only difference is that in the denominator, within the input of the mechanism M, we no longer necessarily have the rankings, the ordinal preferences, but we have some function of the real values. This is some kind of function that could be, depends on the interpretation of what limited information is actually about. Okay, so let me start explaining these things. So the first interpretation is in terms of this axis, from the left to the right. On the left, we have no information at all. And on the right, we have complete information about the preferences. We have the cardinal valuations. And somewhere in the middle, we have the ordinal preferences. And most of the work on the distortion is actually on this model here. As I said before, it makes sense to consider less than ordinal information. What do I mean by that? I mean that maybe in some applications, it doesn't make sense to assume that you have preference to complete rankings over all the possible outcomes. It might be that the possible outcomes are too many, so maybe it makes sense to ask agents to only provide rankings for some of them, either chosen at random or maybe the first K ones or something like this. It could also be the case that you don't ask all the voters for their opinion. Maybe you just ask a subset of the voters, again, because of scalability issues. So there is a lot of work on this part as well. And this is not, again, a complete list. But out of these papers, I will single out the last one because Kamesh will actually talk to us about this on Friday at 10 o'clock. Now, on the other side of the spectrum, we could also have what I call more than ordinal preferences. And the idea here is that agents express their ordinal preferences as before, but maybe there is a way that we can elicit a little bit of cardinal information, some information about the numerical values in order to get better distortion. And the question here is, how much of this information do we need to elicit in order to get meaningful improvements in the distortion in different settings? And there are two recent papers on this topic. And the first one will be presented by Yorgos on Friday, so tune in for this one as well. Now, coming back to this axis, you might have noticed that I have removed the ordinal information from there because, as I said, you don't necessarily have to classify information as being ordinal or cardinal. In truth, maybe there is some kind of different elicitation structure that can receive information from the agents And that information can be either ordinal or cardinal in general. So for example, one such elicitation device is threshold votes. So a threshold vote is a vote in which it's an elicitation device in which you supply a threshold, a value to the agents, and then the agents return all the alternatives that they value higher than this threshold. And this can be together with ordinal information. It could be also can be asked without having access to the ordinal information. And this kind of threshold votes are present in the paper by Gerdes that I advertised earlier. And they're also present in the paper by Umang that will be presented in the next session. But I will not advertise this paper yet. I will advertise it in a few slides in a different context. So, just wait for a bit. And the other way, another thing that can be classified in this axis from left to right is the communication complexity of the problem. So here what happens is that the mechanism asks the agents to provide a specific number of bits of information via constructed queries, carefully constructed queries, and then the agents return these bits of information, and then the mechanism is trying to minimize the distortion based on the information. And here you can actually study the trade-offs between how many bits are communicated and how much you can improve on the distortion of ordinal mechanisms. Sorry, of mechanisms in general. They don't have to be ordinal. So here, Nisar will give us a presentation about these two recent papers. And I have to say that the second one was actually presented in this year's CC. So if you missed that, you should definitely be there for Nisar's talk to see it. I also mentioned at some point that information doesn't really have to be, limited information doesn't really have to be due to the preferences of the agents, but it could be due to the structure of the problem. So let me explain what I mean by that. So imagine a scenario in which we need to make a global decision, but this has to be made, maybe due to scalability issues, organizational issues, it has to be made as a result of aggregating many local decisions. So we can group the agents into, we can partition the agents into groups, and then each group makes a local decision, and then we have to aggregate the results of these local decisions into a global decision. An example could be where we have voters partitioned into districts. Districts select their representatives from the set of all alternatives, and then we aggregate only the representatives somehow using a voting rule into a joint outcome. And here, the important thing is that even if there is no loss of information in the local decision, even if we have exactly, maybe we even know the numerical values in the local decisions, some information is bound to be lost when we move from the local level to the global level. So Alexandros and I have written a couple of papers recently on this topic, and Alexandros will present those today, later on during the last session. And finally, this wouldn't be a workshop at EC if there was no mention to truthfulness and no mention to incentives. So a very fundamental question here is the following. What if on top of the limited information, we also want to ensure that information is revealed truthfully by the agents? And in a sense, it's not enough that we only operate on limited information. Even that information, we have to work for it. We have to somehow convince the agents to give us the right information. And of course here, the loss in efficiency can be due to truthfulness. It can be also due to the loss of information. And the question is, can we design strategy-proof mechanisms that have good distortion? This is quite interesting, and part of the talk that I just advertised by Alexandros will also touch on this. But here's the point where I advertise Umang's talk coming up in the next session. And this will be precisely about this topic, about bounding the welfare of the distortion of truthful voting mechanisms. So this is all I had to say. Thank you very much. And if you have any questions, I will be happy to answer, and I'm sure the other organizers will be happy to answer as well. Thank you.